Okay, so in this video I'm going to go over a little bit about how power relationships work in an AC circuit. So we all know that AC voltage travels in a sine wave. If we have and the way we look at this is it progresses around a graph. If we want to look at it vectorially, it travels around a graph. So we start at 0 degrees, was here, then at 90 degrees, got to here, at 180, got to here, at negative 90 or 240 degrees, the sine wave's here, and then we come back to our starting point, which is 0 degrees again. Okay, so now, if we have a fully resistive load, our current happens at the exact same time, the exact same point in time, right? When we hit our peak of voltage, we're hitting our peak of current. When we hit the peak in the opposite direction, we hit the peak of current in the opposite direction. So what we say is that our resistive current is in phase, which means that there is 0 degrees of displacement between our current and our voltage. So any resistive power is always drawn along our base axis. So our resistive power is going to be here. Now, inductive power, or inductive current, so anything that's through an inductor or whatever, is always going to be 90 degrees behind our voltage, right? Black is our source voltage. So what that means is our inductive current is actually going to hit the peak 90 degrees behind. Right? So when our voltage or our current is at its peak at the same time as our voltage is down here, right? We're 90 degrees behind. So that means that our inductive current lags by 90 degrees. So inductive current is drawn along this axis on a phasor diagram. The other component we can have in an AC circuit is a capacitive current. And capacitive current is always ahead of the voltage, or it leads the voltage by 90 degrees. Right? So our capacitive current is happening at this point. Okay? So what we end up with is, if we have a circuit that's got resistance, inductance, and capacitance all at the same time, we've actually got current that's reaching its peak at different times throughout that cycle. So when we try to determine how much the relationship between how much of our current, or therefore power, is inductive and how much is resistive and how much is capacitive, what we do is we draw that out on we'll draw it out in a minute. What we do is we add all these currents at the vectors that they're in. So if we have a resistor, a resistive value that, let's say, has 200 watts of power, we're going to draw it there. And then if we have an inductor that has, say, let's go with 300. There's 300 watts of induction. We don't actually call them watts because watts is a term for power, right? So instead, how did we find watts? Well, you multiply your current times your voltage, right? The amount of voltage applied times your current will give you your wattage. So when we talk about inductance, it's not actually wattage. What it actually is simply called volts, is volts times amps, and it's reactive because it's reactive power. It's the due to inductance. So we need to know that that's inductance, so we go XL. Okay? It's still calculated by your volts times your amps. Okay? How many volts are applied, how many amps of inductive current do we have? The formula for finding it is exactly the same as it was for watts, only we now refer to it as volt amps, reactive, inductive. Then if we put a capacitor in there that has a VA, because it's the same deal, same kind of thing, it's still volts times amps. And let's say that capacitor is 150 volt amps reactive. Sometimes it's C, they write it as C, sometimes it's XC, then it's happening there. And when you add all of these together, head to tail, we've got induction going this way. Our capacitor is 180 degrees opposite the induction, so what we actually end up doing is subtracting the two, and we end up with a net vars of, in this case it's going to be 150 again. We just call them vars now. They're not inductive or capacitive, it's our net vars, right? Or you can put that it's XL, because it's what's left over of the XL after you take the XC away. We usually just go with vars. What we end up with when you add those two together vectorially is our system VA. Okay? How do we find that? Well, we use Pythagorean's theorem, right? We can go 200 squared minus 150 squared equals, and then take the square root of that to find our VA. $132.29. So our apparent power, or what we see, is 132.29 VA. So this number right here is what can be measured in a circuit by simply connecting a voltmeter and an ammeter and multiplying the two values together. So it's apparent. It's what we can see with common meters. Volts times amps, that gives us our VA. You need a special watt meter to read the wattage rating, right? And we talked about those a little bit in the first year electrician program. Watt meters just measure what's in phase with the voltage, right? VARs, there's no way to measure that. We don't have equipment that can measure our reactive power. We can calculate it. If we know we can use a watt meter and find that we've got 200 watts in a system, and take a voltage and then a current reading, multiply them together and find our VA and calculate the VARs, but there is no way to measure this. Okay? So that's what the power relationships are between an inductive reactive power, capacitive reactive power, and wattage in an AC system.